Today we're going to talk about the QFT Hamiltonian for the free scalar field phi. We're going to do a big recap here. Remember that in quote-unquote ordinary quantum mechanics, we need to mathematically model our physical system in a quantum mechanical framework. This means three big things. One is we need to clearly define our Hilbert space. Two, we need to define what our relevant operators are and the exact mathematical action of these operators on the kets in our Hilbert space. And the third big thing is to postulate the form of our Hamiltonian in terms of the above clearly defined operators. In the first two lectures, we achieved items 1 and 2. We recall defined our Hilbert space as the quote-unquote huge Hilbert space obtained by taking the tensor product of each of the quote local Hilbert spaces at each voxel, where each voxel consisted of a ball on a one-dimensional track. We clearly defined some important operators and their actions on the huge Hilbert space, namely phi of x, pi of x, and the partial derivative of phi at x. We now focus on task 3, establishing h. In the third and fourth lectures, we took our quantum hats off entirely and we imagined that we still had a space filled with one-dimensional balls on tracks, but that the system was entirely classical. We called this scalar field phi of x, and phi of x here was not an operator, it was just a number while we were doing these considerations in lectures 3 and 4. In lecture 3, we argued using special relativity, locality, and simplicity that the Lagrangian had this very simple form. Then, in lecture 4, knowing that our purpose was still to establish h, we used Noether's theorem, a very powerful theorem and a beautiful theorem, to give us the formula to get the Hamiltonian density from the Lagrangian density. That takes us from this Lagrangian density to the Hamiltonian density. Specifically, even though it was a high-level lecture, the summary of it was the following. We defined the Hamiltonian H as that conserved quantity which arises when our system, which had a specified Lagrangian density L, when our system has time translational symmetry and is also quote-unquote confined to some non-infinite value in space. It's limited in space. And then from that Hamiltonian density, we would get h, which is the true Hamiltonian, which is just the integral over space of this Hamiltonian density at each point in space. After all that hard work reviewing Lagrangian mechanics, classical field theory, we got a very simple and beautiful formula for the Hamiltonian. This is, as of now, for a classical scalar field. The Hamiltonian density is equal to this, 1/2 pi squared plus the partial derivative of phi quantity squared taken over x, y, and z coordinates plus m squared phi squared. And remember, our classical arguments gave us this formula for the Hamiltonian density. Now, we want to do quantum field theory, not classical field theory, and all we need to do is basically the following. We simply just postulate that our quantum field theory system, which we talked about with the huge Hilbert space and everything else, and the operators we mentioned, has exactly the same Hamiltonian density, h of x. In this case, when we translate this from classical field theory to our new postulate for quantum field theory, these numbers, pi, phi, and the derivative of phi just end up becoming operators rather than fields. So phi, pi, and the partial derivative of phi simply become operators rather than fields. And these are the operators exactly as we described them in the earlier lectures. They have a very well-defined action on the huge Hilbert space, or the QFT Hilbert space, without any ambiguity. One small quirk is that the Hamiltonian density pi, phi, and the partial derivative of phi were defined as functions not only of space, but also of time t. This is in the previous lectures on classical field theory. These were all functions of space and time. And we used to symbolize that as phi of x without the arrow over it, implying this x has means three spatial coordinates and one time coordinate. So far in our development, of quantum field theory, it is not clear how, for example, phi of x at a given voxel x would evolve in time. We haven't went over that at all as we extended quantum mechanics to quantum field theory. For now, we need not worry about it, and we just assume that equation 1 is just time independent. The Hamiltonian density is time independent, and that's consisting of time independent, well-defined operators phi of x, pi of x, and the partial derivative of phi of x. These are all, we don't need anything, we don't need any consideration of time. We define these very clearly in our original 2 lectures. As of now, the operators don't evolve in time. We'll change that in the future. Armed with all 3 elements, 1, 2, and 3, all those 3 big parts of any quantum mechanical system, we can now explore its various physical features. Now for QFT, we have everything we really want whenever we define a physical system and quantize it. We have our Hilbert space, our operators, and our Hamiltonian. Just like in ordinary quantum mechanics, after we've defined our physical system, Hilbert space, operators, and Hamiltonian, one of our first and most important questions we can ask is, what are the energy eigenstates and eigenvalues of our system? You probably recall from quantum mechanics that this is one of the most important questions you can ask for any system, like the hydrogen atom. It correlates with a lot of important physical findings, and it also helps you understand a lot of physics behind this system as well. And what does that mean? Well, basically, the other way of phrasing that is which kets, and I symbolize it here with an E sub I, satisfy the following: that the Hamiltonian of the system applied to the ket E sub I gives you back the same ket E sub I with some constant number in front of it, which is called the eigenvalue. This is a classic eigenvalue eigenvector equation for the Hamiltonian. So the question is, what are the various EIs that will satisfy this, both in terms of the numbers, the eigenvalue, and in terms of the eigenvectors? This is one of the most fundamental questions you ask after you've fully defined your quantum system, which we now have for QFT. Before we rush, it is worth it to briefly pause and recall a similar problem you should have reviewed in ordinary quantum mechanics: the harmonic oscillator. Just picture we have almost like a ball on a 1D track. Not almost, it is. I just happen to write it horizontally here. And this ball can go left or right. We're just assuming a one-dimensional harmonic oscillator. And for the purposes of this discussion, even though we have little numbers drawn here, little rungs drawn here, let's assume this can take on continuous values, just like you did in ordinary quantum mechanics. The first thing, if you go by my recipe for any quantizing any physical system, is to define the Hilbert space. The Hilbert space is the set of all possible values that our point mass can take on its 1D track. In the continuous representation, we can phrase the kets like this: a ket Q, where Q can take on any real number from minus infinity to positive infinity, and associated with each of those is a potential value you can find for this ball, and associated with that is a ket in our Hilbert space. If you take the set of all linear combinations of this, that is the basis, that is our Hilbert space. So the set of all Q's are the basis for our Hilbert space. This is stating what you've studied a lot of times in quantum mechanics, but just in a very explicit way. By saying it's a basis, we just mean the following: that any ket psi in our Hilbert space can be expressed like this, as a sum over the other of the basis vector kets Q. In this case, it's a continuous sum, so we'd use an integral. Every time we use an integral, we add the factor dx. And then this thing, which is actually called a wave function, is just the coefficient of each of these Q kets. We described our system right now using this basis over here, the Q basis or the position basis. But as with any other vector space, of course, remember, we can always use a different set of basis vectors to describe kets. So I'll just illustrate that geometrically. Let's just say we have a vector here. This is just a old-fashioned a two-dimensional picture of a vector. We can pick our basis vectors, EX and EY, and then we can realize we can coordinatize this vector and say that this is 4 EXs and 3.9 EYs. And we could describe it that way, as you can add 4 EXs plus 3.9 EYs to get this vector in this very primitive, simple 2D vector space. But of course, you can also change your basis vectors to something different, E prime X and E prime Y. And if you did that, you would get a different linear combination of these basis vectors. So the same vector can be described with multiple different basis vectors. And of course, the same thing applies to the Hilbert space of quantum mechanics. We can use a position basis, or we can use any other basis we want. Part number 2 of our recipe for quantizing a quantum mechanical system is to then define the relevant operators. In our simple harmonic oscillator that I have here, with the classic things to define are the position vector, the position operator x, and the momentum operator p. And what are their actions on this particular Hilbert space? We can define them as the action on the basis vectors, and from there we can extrapolate their action on any vector using linearity. So the x operator on the q vector basis just gives you back the same thing by definition, multiplied by the actual position eigenvalue q. The p operator acting on any given ket psi in our Hilbert space gives you this right over here. If you express this ket as this integral sum, as a sum basically over various position uh, uh, basis vectors, all you have to do is take the derivative of the wave function part. This you remember very well from quantum mechanics. The position operator just acts as the derivative times minus I of the wave function, and that gives you your new wave function for the new ket. And then the other thing that we define is an operator relationship for the harmonic oscillator, where if you it will, I'm sure you'll recall that the commutator of x and p gives you I. The third step in our formula is to postulate a Hamiltonian for our physical system. And for the harmonic oscillator, this is the Hamiltonian. The Hamiltonian for the simple harmonic oscillator is just p squared over 2m plus 1/2 m omega squared x squared. And these are operators that have the hats on them. Eventually, I'll start to drop the hats like we do in quantum field theory all the time, but sometimes I'll put them in. Omega squared is just some constant. A lot of times when you just study quantum mechanics, they just start with the Hamiltonian, but technically, to be strict, you have to first define your Hilbert space, define your operators, then talk about the Hamiltonian for it to make any kind of mathematical sense. Then you can ask the question, what are the eigenstates and eigenvalues of the simple harmonic oscillator that satisfy this classic eigenvalue eigenvector equation? And first note that we need a way to express our answer to this question. So what are the eigenstates of our physical system with this Hamiltonian? Well, first we need to pick some sort of a basis to describe our answer, some basis vectors 1, 2, 3, and so on and so forth. And we can say that our eigenstates of our Hamiltonian, E sub I, is equal to some linear combination of those basis vectors. And we're free to choose what basis vectors we want. Let's now pick the position basis vectors, Q, to help describe our answer. We could then really say our goal is to find the coefficient of each basis vector Q. In other words, to find the quote-unquote wave function that satisfies the eigenvalue eigenvector equation for this Hamiltonian. We know how p and x operate on the wave function, and one can say that our task is then to solve the following differential equation. We can use this classic equation to set it up once we know how these things act on the wave function, and this is the differential equation that we get. Here's this differential equation just expressed differently. I'm going over this fast because you should be familiar with this from quantum mechanics. So here we just have a kind of standard differential equation that you might encounter in a differential equations course. And your goal now becomes to just solve this differential equation for psi of x. That's actually not that easy of a differential equation to solve, as you guys may have done that in your quantum mechanics courses. I'm not going to go into how to solve that fully in this basis, in this form here. I'll just tell you that this is the answer, that we get a wave function that has this expression, and these are the eigenvalues. I'm using here I'm storing the h bar, and I just popped this into Gemini to get the actual equation of the simple harmonic oscillator. You can look at any quantum mechanics textbook to look at this. And these uses Hermite polynomials and things like that. The whole point of what I want to say here is that we expressed our solution as some function, psi of x, which represents a linear combination of the position basis vectors. It's a complicated function, but that's the idea. Now, I want to get more into the harmonic oscillator. Remember, we're just still doing regular quantum mechanics again, just reviewing the harmonic oscillator to see what it can teach us about understanding the nature of the QFT problem. You may recall that while we can solve the tough differential equation with the complicated answer in the x basis for the simple harmonic oscillator, the problem can be simplified tremendously by the following trick. You define a new operator called A hat and A dagger, which is just its Hermitian conjugate, as following. You say that A hat is equal to 1 over the square root of 2 times this, a linear combination of the position basis vector x and the momentum basis vector p. And then this is just its Hermitian conjugate. We're going back to units now where h bar is equal to 1. I'll mostly stick with that throughout the course. Once in a while I won't. I'll let you know. If you solve this instead for x and p, you can just do that with some basic algebra. Then you'll get that you can say that x is equal to this in terms of these new operators a and a dagger, and p is equal to this. Now recall that x and p are physical observables, and by the principles of quantum mechanics must be Hermitian operators, but a and a dagger are not. In fact, you can see the Hermitian conjugate of this, and this is not the same as that, so these are not Hermitian. But we can re-express x and p in this form with these defined operators. Now, before we go too far, what is so good about all this? Well, I'll start to show you subtly. But the first thing we want to do is establish what is the commutator between A and A dagger. That'll come into handy in a little bit. The commutator between A and A dagger we can calculate as just a review is this. Definition of the commutator is that. Then we plug this formula for A into here, and then this formula for A dagger into here. Minus sign goes here. Back to the A dagger again goes here, and back to just the A here goes here. And if you expand that out, you get this. And if you just do some algebra and do FOIL, first, outer, inner, last, for these two binomial terms, you get this expression and this expression. If you rehash things a little bit and pull out the 1/2 from both of them, including the minus 1/2, you can just get this one long expression here. This mwx squared will cancel out with this minus mwx squared. This factor for p squared will cancel this factor for p squared. And we're just left with these 4 terms. We can then re-express this as factor out a minus I, and then do xp minus px, which is really nothing but the commutator expressed here. And we could do the same thing right over here. So that's what we get left with. And knowing that, now going back and remembering that xp commutator is just equal to I, that's our postulate of the operators, how they act for this, for everything in quantum mechanics, but certainly for our simple harmonic oscillator. And then we just, since that's I and we have I times minus I, one thing to just remember that comes up over and over again in physics, but certainly in QFT, is minus I times I just gives you the number 1. You get minus I squared, but I squared is -1, so you just get +1. So then this whole thing shakes down a half of 1 plus 1, which is a half of 2, which is just 1, which means that this commutation relationship is true for the simple harmonic oscillator, that A dagger, its commutator, is equal to 1. That helps us if we go back to our H, our Hamiltonian, for our simple harmonic oscillator over here. It allows us to re-express this Hamiltonian in terms of the A and A daggers, as I'll show you now. If I just plug in what P and X are here in terms of these definitions, I'll get this expansion. I have a P squared here, and I just use this entire thing squared and this coefficient squared. That's how I got the that's how I got the x squared part over here, and then the p squared part I take from over here, and I just use FOIL to do a dagger minus a FOIL to get this expansion and this expansion over here. You can just do the algebra there. Certain factors cancel here, the m's. Then this expression for h simplifies as follows. Now, this a dagger will cancel out this a dagger. This minus AA will cancel out this plus AA, and I'm just left with these these 4 terms over here. I could combine the a dagger a's. One a dagger a plus another a dagger a gives me 2 a dagger a's, and same thing with the a daggers. Now, here's where I use the commutation relationship that we derived in the previous slide, that a dagger equals 1. What does that mean? You'll see this all the time in quantum field theory, so make sure you play with this a little bit on your own. But I can change this a dagger. I can flip it around to make it look more like this, an a dagger a, knowing the commutation relation. The commutator of a dagger equals 1. That implies by definition a dagger minus a dagger a equals 1, which of course means if I rearrange things that just the a dagger is equal to 1 plus the a dagger. So every time I see an a dagger, I can replace that with this, which now gives me this for our expression, that it's 1/4 omega, 2a dagger a still stays the same, plus 2, that stays the same. And now instead of doing the a dagger, I use this formula here that I got from my commutation relationship, 1 plus a dagger a. That just continuing out with the algebra gives me this. Expand out the 2. And then now I have these a dagger a's, which can combine as 4 a dagger a's plus the number 2. And then if I just divide by 1/4, this is what I get. The Hamiltonian can be re-expressed in terms of a dagger a's exactly like this. The Hamiltonian for the simple harmonic oscillator, I have omega, and that omega is a dagger a multiplied by the quantity a dagger a plus 1/2. What's so good about that? Well, we have a new formula now for the Hamiltonian in terms of these, abstract a dagger a things instead of the more physically obvious x and p. But what was the point of all that? Well, again, hopefully this is a recap of quantum mechanics for you, but I'm going to keep showing you a little bit more. Well, to understand the utility of that, we still have to work a little harder and take the commutator of h with a dagger. And then if you do that, I just literally put in the formula for h here inside this commutator with a dagger. And then I can get, if I expand these things out, this constant will always pull out from any commutator, so here and here. And then the sum of any two terms in one slot of the commutator can just be expanded out like this. So this is an a dagger a with an a dagger here. And then this 1/2 gets pulled out over here. But the commutator of any real number with an operator is, of course, going to be 0, based on just write out the definition of the commutator, and the numbers will always commute with an operator. So that gives me 0. So I'm left with this over here. And there's a classic formula that also comes up a decent amount in quantum field theory worth remembering, that if you have a commutator of 3 operators, A, B, and C, that are expressed like this, you can pull out the A this way and then stick with the commutator of B and C, plus you pull out the B to the right side here, and you have the commutator of the first and third A and C here. So I apply this formula to this remaining term over here, and this is what I get, that I take the a dagger a, pull it out here, and I still have this with this, and then I take this a, pull it out to the right, and I have a dagger, so that's where I'm at so far. Well, the commutator of something with itself is always 0, and this, from our commutation relations, we'll remember that the commutator of a dagger is just 1. So this whole thing simplifies to this. So this is also true for the commutation of the Hamiltonian with the a dagger, that I get omega a dagger. And similarly, you can play around with the math. Probably good practice to just do it at least once if you haven't done it. That if I take the commutator of Hamiltonian with the a, not with the a dagger, I should get almost the same thing, but a minus sign, minus omega a, not a dagger. Now, these things will help me. Again, we're still trying to figure out what the purpose of all of our work was with defining a dagger a's, and we're starting to get close to what the whole point of this was. Let's suppose that EI, again, is an eigenstate of our Hamiltonian H. Let us investigate this state. You used to have a Hamiltonian of the eigenstate H, and then apply the operator a dagger to it. Let's see what happens. There's something interesting that'll happen. So I applied a dagger to EI, to my Hamiltonian eigenstate, and then I just hit the Hamiltonian with it again, and let's see what happens. Well, then I get this H a dagger, but I can get rid of these parentheses. This is just nothing but H a dagger without the parentheses there. And H a dagger, from the previous slide, you'll recall, has a commutator relationship that we just derived. And that commutator relationship allows us to express things like this, that H a dagger is equal to omega a dagger plus a dagger H. So I can change this to this, which is what I've done here, and expanded it here. Okay, keep working through the math here. I can distribute this over the EI kets, as I did here and here. Well, now by definition, EI, the supposition that we started with, was an eigenstate of the Hamiltonian. That's what I'm starting with. So H hitting on EI just gives me EI back with its eigenvalue pulled in front, right over here. This part still stays the same. And this EI is just a number, so I can move that wherever I want. So I can pull the EI out here and just put the a dagger over here. So this is the final expression I'm getting here. And of course, I can factor out an A dagger EI, which is the same in both terms, and get this final expression. What this means is that I start with A dagger EI, hit it with the Hamiltonian, and I still just get A dagger EI, but just multiplied by some number. And this number is whatever EI was, which is the original energy, plus omega. So what this means is that this thing, A dagger EI, is also an eigenstate of H, but with an eigenvalue raised, quote unquote, raised by the value omega. For this reason, we call A dagger a quote unquote raising operator, or since it effectively creates a unit of energy omega, we will also call it a creation operator. And this will be the term that comes into real play in quantum field theory. A dagger effectively acts as a creation operator in that it takes an eigenstate and brings you another eigenstate with an eigenvalue a little bit higher by the factor omega, at least here for this simple harmonic oscillator. We haven't gotten to QFT yet. In the same way, we can show that not A dagger operating on the eigenket E sub I is also an eigenstate of H, but with an eigenvalue lowered by the amount omega. This is probably worth just reproducing if you haven't seen it or done it recently in quantum mechanics. So in other words, H acting on A E sub I gives me A E sub I again, but with the eigenvalue that's one less by omega. That's one unit of omega less than the original EI. And that's why this A is called either a lowering operator or a destruction operator, which is the term we'll end up using in QFT. Still not doing QFT right now. Still on simple harmonic oscillator quantum mechanic treatment. Now, note that though we may not have yet exactly solved the eigenvector eigenvalue problem, as well as we did with the position basis and the Hermite polynomials using our trick, we still learned that given an eigenvalue eigenstate, we can find other eigenvalues by simply adding and subtracting omega or acting with A dagger or A. So we have a way to build up eigenvalues and eigenvectors. We didn't tell you what the zeroth one or the ground state was, so we might go up and down. We haven't proved that these are the only eigenvectors and eigenvalues, but we're not going to go there. I just want you to emphasize that our trick was very helpful here at learning a lot about our system. And rather than dealing with these complex Hermite polynomials, our trick was very helpful. And what was the trick? Our trick was to re-express X and P via new operators that were not Hermitian called A and A dagger. Just remember that trick. Let's go back to QFT. We were just going back to quantum mechanics. And again, every time you think of QFT, I want you to basically start to immediately think of an XYZ space and a bunch of voxels in space. And each voxel has a ball going up and down on a 1D track, which we can quantize in the ways we've talked about before. And there's a bunch of operators at each voxel called phi of x, pi of x, and the partial derivative of phi with respect to the spatial coordinate. Recall that one particular set of basis vectors for our quote-unquote huge Hilbert space, which I'm going to continue to now call the quantum field theory Hilbert space instead of using the language huge Hilbert space, we'll just call it the QFT Hilbert space, is this. You don't see this that often in books, but I think it's important to make sure that things are clear and we're not doing something magically different than quantum mechanics to go over this. So when you write it out, it's kind of crazy to write it out that I start with voxel 1, voxel 2, all the way to voxel n to the third, which is an enormous number. And within each voxel, I put the actual position basis. This entire thing here, again, is just one ket in our huge Hilbert space or our QFT Hilbert space. The set of all kets means I have to keep varying each of these q's, either in a discrete or continuous fashion. The enormous set of all possible tensor products we obtain by represents our entire basis for the QFT Hilbert space. Good, that's what I just said. This means, of course, that any ket psi in our QFT Hilbert space can be expressed as a linear combination of these basis vectors. So any ket that we're looking for is some linear combination of all of these, which if you wrote out, which would be massive, you have to keep changing q for each one of these in every combination and write them all out as a sum. And then when you find put a coefficient in front of each of those, you get one ket in our huge Hilbert space or our QFT Hilbert space that would be called psi. It's important to remember that. And the physical picture, which we've talked about before, is you have a superposition of configuration states. You have the ball going up and down on 1D track at every given point in space. That's just one configuration. Then you change one configuration, even just in one voxel, then you get a different configuration. You imagine changing all the possible configurations and having a linear combination of those, and that's one ket in our huge Hilbert space. That's the physical picture. And recall, our big problem right now is still to find all the kets, which I symbolize like this, EI of QFT, that satisfy this equation. That the Hamiltonian of QFT, which we started off by introducing as a natural extrapolation of our scalar field derived Hamiltonian, hitting on our eigenvector that we're looking for, EI, the eigenvector, the energy eigenvector for QFT, is supposed to give us back the same exact vector multiplied by its eigenvalue. Our goal is to find out what are the EIs for the kets and what are the EIs eigenvalues, just kind of re-expressing what we started with here. Remember, we can pick an answer to which we want an answer, and you can pick this particular basis vector. Sometimes it's good. You won't see, but we're going to use a trick in quantum field theory. You'll almost never see this talked about, but you should, because I want you to understand the physical picture is a bunch of balls going up and down in space on a 1D track. That, for whatever reason, is the picture of nature, at least at the level of the scalar field theory that we've done. And we can theoretically express every answer like that. Just like for the simple harmonic oscillator, we can express the answer in the position basis, and we understand it intuitively. And then but the formula was complicated with Hermite polynomials and things like that. We could, in principle, express our answer this way. I'm just kind of hammering home that point. If you really want, you can define a wave function. We've talked about this before, which basically this is the coefficient of each of these basis vectors. So you plug in what each of these q's are for all n to the third slots, and you give me a complex number. And then you do that constantly. So you basically have a function, a multivariable function of n to the third variables that just generates a complex number. And with this Hamiltonian, and you can just kind of rephrase this as a massive differential equation type problem. We're going to actually tackle this in the next lecture, not this lecture, using our trick. But before we do, just to make sure that the problem is well defined mathematically, I think it's worth just emphasizing things. When I've studied quantum field theory, there seemed to be a lot of big jumps, things weren't mentioned, and I started realizing later that you can define things very well mathematically. There's a few problems that occur later, which we'll talk about a little bit here in this quantum field theory course and maybe our next one, but so far we're pretty clearly defined mathematically. We haven't done anything bad. Just to show this, before we do, let's make sure that this whole problem is well defined. We basically, in order to do this, instructive to imagine that someone gives us a proposed solution. How do we check it? It's always a good way to know that the problem is well defined if you can check what the proposed answer is. Well, a solution can just be described as the full function psi. This is a massive wave function of all these multivariables. And we know how phi, pi, and the partial derivative acts on vectors in our QFT Hilbert space. How about on the wave function, if we just imagine a big differential equation and get out of our Hilbert space and just think of more differential equation type stuff? How do each of these guys act there? Well, it's not hard to imagine. Once you know how they act on the vectors, you should very much extrapolate how they act on the wave function. You can kind of skip this part, or just if you want to play around with it, think about it a little bit. It's not hard to realize the following thing, that if I want to see what phi does to the wave function psi, the massive wave function psi, all I have to do is, remember, phi of x is a different operator depending on which voxel I derived it from. It was promoted so that it's defined on the huge Hilbert space, or the QFT Hilbert space, but technically there's a different operator from each voxel. If I grab it from voxel x, all I do is I take the q of that voxel x and I put it in front of this psi, and that's how it modifies psi. And that tells me how we'll change psi entirely. The pi operator just acts like the derivative, like it did in ordinary quantum mechanics, and you have to be careful of which derivative you're talking about. I kind of explain that here. You can pause the video and look at it, but the idea is that you look at a psi at a particular q voxel. What psi is at the very next step up, meaning you stay in that voxel, but think about going to the next step up, the next q up, and see what the psi is for that one. I mean, the whole thing is expanded in a massive basis. You subtract the two and divide it by the rung spacing if you're doing discrete things, and then that's the new coefficient for the original q voxel, and that gives you the formula for how to change every voxel, and that officially gives you how to change the wave function. So you can stop, pause, and think about this. Sometimes I do it like while I'm driving, when I don't have a book in front of me, just to reimagine how these things work. And it's worth it to create that mental structure in your brain. Once you have the mental structure, you're ready to play. You know where everything is, and we're ready to go with the next steps. You may also ask this question. requires a little bit of thought and thinking again, but the partial derivative of phi is a different operator that still should act on the wave function. It's different than the momentum, and the idea is that this is between voxels, and this is within the same voxel. You could think of it like that. That here what happens is this kind of idea here, that I'll find two different elements, basis vector elements that are quote unquote next to each other by voxels by only looking at, for example, if I start with the voxel x, I look at its immediately adjacent voxel in the I direction, and I find the position vector of that minus the position vector of this one divided by the voxel spacing dx. I wouldn't worry too much about this, but you can take your time and look at this, and I think this is right how I put this in there. Just so you know, the whole point of all of this is that everything is well defined mathematically. Our Hilbert space, we can theoretically change this entire question of what are our eigenstates, eigenvalues of the Hamiltonian for QFT. We can make it a big differential equation if we wanted. We can choose and pick. The biggest point is we know now that our problem is well defined mathematically, and we still haven't gotten to the final question of how do we solve the eigenvector, eigenvalue, eigenvector equation for QFT. We'll do that in the next lecture, and to do that, after all this talk about position basis vectors, just to make sure it's clear and you have a physical picture, I actually won't do it in that basis, but I'll use a similar A and A dagger trick that we did here, and that'll give us a very powerful and very insightful way to understand what's going on in QFT.